Good morning, dear conference chairman, dear participants, ladies and gentlemen. My name is Senji Pei from China. Today, I'm very happy to be a conference keynote speaker to present my keynote speech here. Due to limited travel, I could not come to Bangkok to be the conference site. Today, I'm going to give a video presentation for my keynote speech. I'm going to talk about vital role for ethnobiology in new era of biodiversity conservation in China. The speech will include the following three parts. Part 1, an introduction about biodiversity in China. Biodiversity is defined as variability among organisms from our sources, and it includes diversity of three levels of gene, species, and ecosystems by the definition of CDB. China is endowed with 11% of the plant species and 14% of all animals in the earth. According to the updated data, the total biospecies of China accounts for 2,280 species, including animal 54,359, plant species 37,793, fungi species 12,506 species. The main type of the terrestrial ecosystem, including forest, shrub, meadow, steppe, desert, wetland, marine, and farming systems. Biodiversity is the foundation for survival of the development of human beings. China, with its ancient civilization and a history of several millennia, has developed a wide variety of crops and domestic animal, plants, breedings, including soybean, tea, rice, and others. At least 136 cultivated plants originate from China, making up 20% of the world's total cultivated plants around the world and their economic importance, which are important components of global bank of gene banks in the world. China has a variety of useful and economic plants, totaling account about 20,000, of which 11,000 of medicinal plants used in traditional Chinese medicine. China also provides great opportunity for garden plant development in the world. 31,000 flowering plants are now grown in the gardens of the world, so that Professor Wilson said, China is the mother of the garden. Chinese biodiversity make significant contribution to the world economy. Part 2, progress and achievements of biodiversity conservation in China. Over the last half century, China has experienced great social, political, and economic changes that brought about tremendous impact on the environment and biodiversity of China. Also, China boasts abundant biodiversity. This biodiversity is being seriously depleted. About 6,640 fungi and flora species listed in CITES, 4,400 species of plants, and 5,000 more animal species are in the China species red list. Wild plant endangered ratio is 15 to 20%, of which gymnosperma and orchids are as high as 4%. 233 vertebrates are facing endangered. About 44 of the wild species population decreased. To face the challenge of biodiversity-threatened situation, China has made great efforts to protect its biodiversity. In the last 2 decades, in 1994, government of China launched the Biodiversity Conservation Action Plan, and in September of 2010, launched the National Biodiversity Conservation Strategy and Action Plan, as well as many other policies and national actions adopted to combat of habitat destruction, overexploitation, and declining of biodiversity, environment pollution, and ecosystem degradations. Since the year 2000, biodiversity conservation has been upgraded to a national strategy and incorporated into top-level design with law and regulations. Adopted a number of conservation strategies, improved management and coordination mechanisms and capacity building, and conduct scientific investigation, research, and monitoring of biodiversity. Major progress and achievements in this regard are highlighted as following 6 parts. Part 1. National Protected Area System established for in-situ conservation of biodiversity. By the end 2020, China has established 12,000 national parks, natural reserves, occupying the country's land area 18% and covering 90% of the China ecosystem types, 89% of the wild plants and animal species. Mainly priority species of plants and wildlife populations are increased, such as the giant panda, golden monkey, alligator silensis, and tree fern species, taxus, Davidia, parasuria, medicinal orchids, etc. Part 2. A countrywide ex-situ conservation network is being formulated. Before 1983, China established only 22 botanical gardens, including Nanjing Botanical Garden, established in 1929. And up to 2008, China has established 240 zoo display area and 234 botanical gardens and arboretums, 2 national long-term crop germplasm bank, 25 middle-term banks, and other germplasm gene banks, and 14 national germplasm nurseries, as well as livestock, poultry, gene banks, etc., totaling protected 105,724 accessions. In this collection, 39 crop wild relatives originated protected area also established. A countrywide ex-situ biodiversity conservation network is being formulated in China. Part 3. Scientific research activities in supporting biodiversity conservation and monitoring. Chinese Academy of Sciences has played a leading role in field survey of biodiversity, compilation of flora of China and fauna of China, assessment and compilation of China red list from time to time, established monitoring network consisting of 90 monitoring stations in China for monitoring of biodiversity. And biodiversity-related database development and monitoring. It has established a specimen collection system with 25 preservation units containing 16.3 million specimens, accesses, and a comprehensive biodiversity information system, established as well as GEM-Plus Bank of Wild Plants and Animals at KIB, China, as my home institute in Kunming. Part 4. Forest cover and afforestation area significantly increased. Up to the year 2020, forest cover of China has been increased to 23.04%, occupying about 230 million hectares of the land area of China, and the afforestation land area has completed 6.7 million hectares. Desert vegetation reconstruction, 2 million hectares. 50% of China's wetland area are now under protection. In urban area, forest city number reached to 441 cities. Urban Greenland area reached to 14.8 square meter per person. Forest cover rapidly increased in China in recent years has made an important contribution to biodiversity conservation and global climate change. Part 5 of the progress. As development of wild plant cultivation technology and applied in production to reduce pressure on biodiversity. China uses thousands of wild plants and fungi species for food, healthcare, and industry supplies that increased year by year. With advances of science and technology, in particular, technologies of domestication, cultivation, wild plants, and fungi, including use of biotechnologies in selection, breeding, propagation, cultivation, and processing, etc. The number of cultivated plant biospecies and products are rapidly increased. For instance, the harvesting of medicinal orchids from wild habitat to become cultivation land in the last 20 years has been changed remarkably. The common used orchid species in traditional Chinese medicine, including Dendrobium officinale, Gastrodia elata, Bletia striata, etc., are now completely supplied from cultivation land rather than harvesting from wild. An estimated commercial value is over several billion US dollars per year. According to updated data, annual production of Dendrobium officinale is 15,000 tons. Gastrodia tuber is 105,704 tons. And Bletia stricta roots production is about 7,000 tons per year. In recent cultivation, medicinal orchids, Loctochinus formosala has been rapidly developed in South China and with very high value in health care. Cultivation of wild food plants, such as wild vegetables, health food, and other herbal plants and fungi are now under development, are rapidly developed in China too. Part 6. Development and implementation of legal system for biodiversity. Since 1994, biodiversity legal system has been established and implemented. For example, policies on control of illegal trading and smuggling of wildlife and wild plants listed in CITES. In 2006, government launched a policy on equal compensation regulations to establish an equal compensation system covering forest, grassland, wetland, desert, and oceans, which policy have guaranteed priority natural habitat area for biodiversity and eco-service function areas under strict protection by law and red lines. More recently, China implementation of CDB and the Nagoya Protocol on access to genetic resources and the fair and equitable sharing of benefits arising from their utilization to the Convention on Biological Diversity has made progress on related law and at provincial level and prefecture level and conducting demonstration areas, case studies in several communities in different areas with encouraged progress has been made. So the third part of my presentation is ethnobiology and its vital role in new era of biodiversity conservation in China. Ethnobiology is defined as the scientific study of dynamic relationships among people, biota, and environment. It is a multidisciplinary and across-cultural field of science which allowing scientists to focus on complex interactions and dynamic integrations among human and natural systems, enhancing its intellectual merits and broad impact. Biodiversity is the product of the interaction of Earth's life and the environment, which is a natural process of biodiversity change over billion years. However, since human beings entered into Anthropocene era and the industrial societies, the changes of natural process accelerated by human activities, mainly caused by habitat change and our exploitation of natural resources leading to loss of biodiversity. Today, the biodiversity extinction speed is even accelerated than any time in human history. Earth's biodiversity faces crises that threaten to all mankind. The fundamental research of ethnobiology is the study of human interactions with plants, animals, fungi, ecosystem, with focus on traditional botanical, ecological, and medical knowledge of people in different cultures for sustainable development. Ethnobiology reflects this science of nature people-based subject and closely linked practices of biodiversity resource management. Therefore, it has a vital role for biodiversity conservation in China and the world. Since the 1980s, ethnobiology has been introduced and developed in China as an interdisciplinary research field covering research subjects, ethnobotany, ethnomedicine, and ethnoecology, etc. Research activities including documentation, evaluation, and application of traditional knowledge into utilization and management of biological resources for sustainable development and healthcare. Current global concerns, including food security, climate change, biodiversity conservation, and human health. Ethnobiology study can provide insights into ways that societies interact locally with their environment resources and also be able to help societies to bring together and integrate local knowledge and scientific knowledge to advance the cause of achieving biocultural conservation, which is particularly significant for the biocultural diversity-rich countries like China. In October 11 to 24th of this year, China is going to schedule the 15th meeting of the Conference of the Parties of the Convention on Biological Diversity, that's COP15. In Kunming, southwest China, Yunnan province, where the participants' nations are expected to address challenges in biodiversity conservation, and COP15 with the theme ecological civilization, building a sharing future for all life on Earth. We are faced today with a worldwide COVID-19 pandemic. The outbreak of this disease is connected to both ecological and human systems, demonstrating the importance of paying attention to the connections, the two, in dealing with the issues of human survival. Similarly, human faces other crises at present that related to both ecological and human societies, including additional diseases, food, water, climate change, and others. At the same time, there are benefits derived from the ways that biodiversity regulated the ecosystem. Humans must now quickly develop the science of survival. With this consideration, we believe that the ethnobiology as a science can play a vital role and make a contribution in new era of biodiversity conservation in China and the world in area of, number one, documentation of traditional knowledge in use of biodiverse species and ecosystem and its management practices. Number two, application of ethnobiological knowledge and traditional techniques incorporated with contemporary technologies into rural community revitalization and biocultural conservation activities in order to improve rural livelihood and eco-safety. Number three, supporting to implementation of CDB and Nagoya Protocol on access to genetic resources and the fair and equitable sharing of benefit fats erosion from their utilization to the Convention on Biological Diversity to promote biodiversity conservation, mainstreaming, and business sector participation in biodiversity conservation. It is believed that with the new era of the eco-civilization reconstruction for building a sharing future for our life on Earth, with our efforts to integrate conservation and development together to meet the challenges we face, a better future is expected to achieve more in the new era of globalization and global climate change accelerated. Finally, I wish the Biotech 2021 in Bangkok will be good and great successful. Thank you very much for your attention. Thank you.
Hi, my name is Gail Volk, and I'm with the USDA ARS National Plant Germplasm System, located at the National Laboratory for Genetic Resources Preservation in Fort Collins, Colorado, USA. Today I'm going to be speaking about plant cryopreservation, research implementation, and outreach. And I'd like to thank the organizers for giving me this opportunity. The USDA has an extensive plant gene bank located at 20 locations throughout the United States. And this map shows the locations of our gene bank field sites. In the middle, you can see Fort Collins, and that's where I'm located. Our National Plant Germplasm System has nearly 600,000 plant accessions that represent about 2,500 different genera stored at our 20 locations. We have about 557,000 accessions that we consider to be seed propagated. These are grown as seed and stored as seed and regenerated as needed. It makes about 93% of our national collection. But we have about 40,000 accessions that are vegetatively propagated. These are our fruits and nut crops, some vegetables, grasses, some other crops such as cacao, hops, and rubber, as well as ornamentals. And these tend to be really challenging accessions for us to maintain. These collections are propagated by grafting or cuttings rather than from seeds. And we do our gene bank maintenance in fields, greenhouses, screenhouses, or in tissue culture. It's really labor intensive. These crops tend to have high economic values. They're nutritious, they add variety to diets, and provide job opportunities for local and or international consumption. There's a lot of challenges in maintaining these clonal collections. We've got a total of 163 crop collections that we maintain clonally. And this means we've got to be in the field working with these plants pretty much year-round. They're especially susceptible to pests and diseases. They're vulnerable to weather events such as hurricanes, heat, or drought. They have to be periodically repropagated, ranging anything from annually for garlic or every 20 years or so for apple. We also have a very wide range in diversity in these crop plants, as well as their abiotic and biotic responses. They have a range of phenologies, growth habits, rootstocks, and more. And even for distribution, it's a challenge because each crop gets distributed using different types of propagules, and rarely is it the seeds. Across the bottom here, I show some diseases that we are struggling with in the United States and that could affect our plant collections. One is citrus greening, another is fire blight, another one is the emerald ash borer insect. It's really important that we secure these clonal collections. It's expensive, but it's critical. This could be done in several different ways. We could have duplicate plantings at multiple locations. Sometimes we can store the seeds for crop wild relative species. Sometimes we put plants in tissue culture and we store them as secondary plants in tissue culture. And if they can survive, they could even be put at reduced temperatures so they don't have to be propagated as often. Our preferred method for long-term securing of our collections is by using cryopreservation in liquid nitrogen. Our facility in Fort Collins serves as the backup location for plant materials in the National Plant Germplasm System. We have about 82% of our seed accessions secured at our location and only about 15% of the clonal accessions secured. The facility has liquid nitrogen tanks where we store clonal shoot tips and dormant buds, as well as embryonic axes, some seeds, and pollen. And we also have -18 freezers for our orthodox seed storage. Our strategy is that we keep our plants at the active sites all around the country where they grow best. And those accessions are then provided as materials for cryopreservation, whether that be dormant buds or pollen or seeds, or even as in vitro plants for multiplication and subsequent shoot tip cryopreservation. Materials are then cryopreserved and stored at NLGRP. This is a chart that shows the collections we have cryopreserved in our liquid nitrogen tanks at this time. We have, over the years, processed a number of different crop plants, either as shoot tips or as dormant buds. Our shoot tips include large collections such as garlic and strawberry and sweet potato, pears, currants, raspberry, potatoes, and citrus. And our dormant bud collection is especially large with over 2,000 different cultivars of apple. In all, we have about 4,500 accessions in our gene bank that have been cryopreserved, which is about 12% of our collections. I'm going to give some examples of some of the crops we've successfully cryopreserved. Our apple dormant bud project has been going on since the late 1980s, when the method was developed in collaboration with university partners. Dormant buds are collected midwinter from field trees of apple in our collections. They're dried, slow cooled, and placed into liquid nitrogen vapor. The buds can then be recovered by grafting. And this method was actually put into place to back up our national collection in the 1990s. Here's an illustration of the process. You can see these twigs in the upper left that are single node sections that have been cut, and then they are dried to about 30% moisture content, and then they're slow cooled to minus 30 degrees in a slow cooling machine, and then plunged into liquid nitrogen for long-term storage. When we want to recover them, we can warm them, moisten them in peat moss for a week or two, and then graft them to assess their viability. All in all, we have over 2,000 different apple accessions, representing 49 different taxa that we've cryopreserved, and we keep in our cryo tanks. To my knowledge, this is the largest clonally propagated collection in the world of plants. And this is work that is coordinated quite a bit with our partner Maria Jenderic, who is the curator for our national collection for the clonal crops at NLGRP. This is just a slide that shows a number of the crops that I've been involved with over the years, performing cryopreservation research that has led to implementation in our national collection. We've developed methods for citrus shoot tips, grapes, garlic, Jerusalem artichokes, as well as willow dormant buds, and pollen for date palms and prunus. Here's a slide about our citrus shoot tip cryopreservation efforts. It's a technology we developed in collaboration with folks in Riverside, California, starting in around 2012. We excise shoot tips directly from surface sterilized buds from plants grown in this greenhouse. And then those shoot tips are then treated with cryoprotectants, cryopreserved, and recovered by micrografting. And we've now used this method for over 400 citrus accessions at our facility. We've also developed a method for grape shoot tip cryopreservation. We establish our plants, our cultivars, in tissue culture. We excise 1 millimeter shoot tips from nodal sections, treat them with cryoprotectants, and recover them by plating onto medium. And we currently have about 20 grape accessions that we've successfully cryopreserved using this method. Over the years, we've been working to adopt protocols from other labs and that are in the literature. And sometimes this can be easier said than done. And we run into a lot of colleagues who are struggling with some of the same problems. In this case, in the past couple years actually, we've added mint, strawberry, and kiwi fruit cryopreservation projects to our lab. And we've used methods that are available either from other locations or that are published in the literature. In this case, we've identified the methods we want to try. We've obtained plant materials for use. We go through a process of practicing a shoot tip excision and regrowth to ensure that our media are good and that our plants are behaving as expected, and that we can get high quality shoot tips that regenerate into plants. And then we'll go through a testing process where we compare one or more different cryopreservation methods using several different cultivars in a with or without liquid nitrogen environment. And in some cases, we've expanded that testing to include wild species, if it turns out we have a lot of wild species we'd also like to cryopreserve. So this is an image of some plants that we've cryopreserved using other folks' methods and adopting them in our laboratory. So there's a lot of challenges for cryopreserving clonally propagated collections. You need to have specialized facilities. You need to have staff that are very skilled in what they do, which may require special training. The work itself is very labor intensive. Our technicians, for a relatively easy crop for shoot tips, can cryopreserve about 60 to 75 accessions per year. And if they're processing dormant buds and the plant materials are readily available, they can do about 100 to 200 or so dormant bud accessions of plants per year. Sometimes the challenge is to have sufficient plant material available, both in quantity and quality, and finding a way to minimize or reduce or eliminate the effects of endophytes, which may considerably hamper the process. It's also critical that we have tissue culture and cryopreservation methods available and tested. And in many cases, we don't have these methods available for crops in our national collections, particularly those of tropical origin. So our future efforts are going to be focused on improving the processing and documentation pipelines for our existing crops. We need to improve our prioritization crops, both within the crop itself, as well as amongst all the crops we have, so we get the right balance between backing up collections that we have good methods for, as well as adding new methods and new crops to our backup process. We need to start putting more emphasis on our tropical crops because they aren't sufficiently backed up. And in many cases, this may involve overcoming the endophyte problem because many of our tropical crops have endophytes that could reduce our ability to be successfully cryopreserving it. For the last part of my presentation, I'm going to talk about some online educational resources that we're developing that are going to be freely available. This is a new website. You can see the location below. It's grin-u.org. And this is an educational training website that has material available in a number of different types of content, including ebooks, videos, webinars, infographics, classes, and more. And we welcome folks to use the content that we've uploaded and that we will continue to upload as we develop it for university instruction and for training within research and gene bank locations. We've developed some infographics, and these are some fun ones. One about gene banks and conservation, one about plant breeding and how plant genetic resources are valuable for global food security. And these first two infographics are actually available in a number of different languages. We have a third infographic about botanic gardens and their valuable role in conserving plant genetic resources. And this one will soon be available in English, French, and Spanish. These are some of the ebook titles that we have posted on our GrinU website right now. The first one I'm going to spend a few more slides talking about because it's about training in plant genetic resources and cryopreserving clonal propagules. We also have one that's a field tour of our Davis USDA National Gene Bank. And we have a couple, one on fundamentals of plant gene banking and one on plant pathology that only have one chapter each right now, but they're quickly going to be expanded as soon as we get the content released. And we also have one on crop wild relatives, and it just touches the surface of all the interesting topics relating to crop wild relatives. And again, there's a lot more work happening behind the scenes. This is the current table of contents for our cryopreservation ebook. And you can see that we have information about introducing plant material into tissue culture, about reduced temperature storage of plants in tissue culture, shoot tip cryopreservation, as well as a chapter on dormant bud cryopreservation. The nice thing about these ebooks is that it's really easy for us to add additional chapters. So as we develop more content, we'll be adding more chapters to this ebook. Here is an example of one of our ebook chapters. It's just a couple pages from it, and this is about strawberry shoot tip cryopreservation using a droplet vitrification method. And in this case, my technician and a collaborator in Oregon and I co-authored this chapter together. It starts off with an introduction to the crop. It has images, it has text, it has downloadable PDFs for methods, both for cryopreservation and recovery, and it has embedded videos. So we have a video talking about an introduction to the crop. It has another one about dissecting plants and preparing strawberry plants for a pre-treatment process, as well as detailed videos demonstrating the shoot tip excision process. So every step of the cryopreservation protocol is described as well as presented in the form of videos. We also have a YouTube site. It's called Grin U Education, and we have a number of videos on it, and we're always adding more. In this case, there are 28 videos talking about domestication and diversity of various crop plants. So we welcome you to access those educational resources and to make use of them in your programs, and feel free to contact us if you have suggestions for improvements or additional topics you'd like to have covered. And with that, I'd like to conclude and thank you for your attention and show a picture of my lab group as of last year when we were pre-COVID times. So thank you for the opportunity, and I look forward to your questions.
Ladies and gentlemen, good morning to all. I welcome you to all to this International Symposium, Biotech 2021, Mahidol University, Bangkok. I am Professor Qasim from Acharya Nagarjuna University, India. I deem it a great privilege to stand before you and to deliver my presentation on in vitro multiplication of some selected banana cultivars, Mesa species from India, and their genetic fidelity using SSR markers. So in this paper, I would like to talk about two aspects here. One is the macropropagation of the selected banana cultivars, and second one is the genetic fidelity studies of in vitro derived plants, and then so this data should be compared with that of the mother plant. So as you know that the banana is a tropical fruit, belongs to the genus Musa, family Musaceae. Its global production accounts for 1 or 2 million metric tons according to FAO. So majority of cultivated banana cultivars are derived from the interspecific crosses between the two wild diploid species, namely Mesa acuminata and Mesa bulbiciana. So banana fruit is a good source of the minerals such as potassium, phosphorus, calcium and magnesium. Its fruit is very easily digestive, and then it has a antioxidant and laxative properties. So it has good therapeutic properties. It is expected to treating the various cancer diseases like colorectal cancer, breast cancer, and general cell carcinoma. So in India, the annual requirement of banana is about 109 billion plants, but aggregate production capacity in India on commercial basis is estimated to be 150 million tissue culture plants only per annum. So there is a huge gap required in the tissue culture production of the banana plants. So there is a need to improve the tissue culture protocols of local popular cultivars available in the southern India, especially on the place. So we have formulated 3 objectives here. So the first one is to improve the quality of banana saplings in order to supply them to the farming community in a cost-effective way. So we are developing the protocols in such a way that that should be cost-effective, and then so this should be supplied to the farming community in the cost-effective way. So the second objective is to investigate the different initiation and multiplication media using various concentration of the BAP and fixed concentration of auxin for commercial production of selected banana cultivars available in southern India. So these are the cultivars that are the Grand 9A, G9, Manthan, and Red Banana. The next one is to test the clonal genetic fidelity of in vitro derived plants. ISSR markers have been employed and then compared it with that of the mother plant. So here we have collected the banana cultivars from the southern India, especially from Bangalore and then Mysore. So these spot suckers were collected and washed thoroughly. So these spot suckers were collected from the field-grown plants. So the suckers are the downside, and then these are surface allied. So these have been used as a plant for regenerating plants. So from these regenerative plants, so these are the plants from this, we have collected the short suckers and then regenerated plants. So from this regenerative plants, we have collected this shoot apices of 2 centimeter size. So these shoot apices have been used as a plant for multiplication purpose. For multiplication, initiation multiplication purpose, we have used this various media with various concentration of BAP and the fixed concentration of IAA. So these various concentration of BAP have been designated as various media like M1, M2, M3, M4, M5. Say you can say M5 consists of the 1 mg BAP with a fixed concentration of IAA, then M4 with 2 mg per liter BAP, then M3 is with 3 mg per liter BAP. M2 is having this BAP of 5 mg per liter with a fixed concentration of IAA. Similarly, M1 it is having the 10 mg per liter BAP with the fixed concentration of the IAA. So like this M2 to M5, so various media have been employed for initiation and multiplication purpose. So these are the shoot apices that are inoculated under the multiplication medium. So these shoot apices were collected and then these are taken at the 2 to 4 centimeter size, and then so these are inoculated under the initiation and multiplication medium. Once the cultures attain their full growth by 4 weeks, so these are ready for subculturing and retransferred to the same multiplication media. After successive subculturing tries, the slightly elongated shoot for transfer to the MS basal medium, supplemented with 1% activated charcoal and also 1 mg per liter of BAP for further elongation of shooting and then rooting to obtain the complete regenerated plants. For the genetic fidelity studies, we have been employed the ISSR markers. So in this, the in vitro derived plants from 6th and 8th cycle of the Grand 9A, Manthan and Red Banana were selected for genetic fidelity studies. So leaf samples were collected, and then from this we have isolated the DNA. C-tap technique have been employed for this DNA isolation. Then 20 ICs or markers we have taken and then screened for cultivars to select the best primers. Finally, 6 primers were collected, and then these primers have been used for to assess the genetic validity of the regenerated plants. So that is compared with that of mother plant. PCR has been carried out on the amplified products for scored of a binary code as present or absent. So these are the nucleated sequences we have adopted, we have taken. So only 6 primers selected for this genetic validity studies. So the results from this experiments, you can see all the shoot tip plants inoculated in the in-situ medium started responding within 15 days under the given conditions. So there is a slight blocking was noticed in these plants, but these are overcome by activated charcoal. So these plants exhibited a varied growth response, and it is categorized into 4 types based on the ability to unfold the leaf bases and turn into a green color. So these growth responses have been designated into 4 types here. The excellent one, which is marked with the plus like this. So the response is within the 2 to 3 weeks of the inoculation. Whereas very good, in which the growth response is 3 to 4 weeks of inoculation. Then it is a good type where the growth response is within the 4 weeks of inoculation. In some cases, when there is no growth here, that is no response at all. So these are the average number of elongated shoots taken by running the 3 cycles, first cycle and then second cycle, third multiplication cycle. From this, we have taken this average number of elongated shoots. Among this medium we have employed here, M5 medium is showing highest number of elongated shoots, that is 3.50. So if the growth is excellent one, that means the plant growth response is recorded within the 2 to 3 weeks time. So the culture quality is very good in this grade 9A. This is followed by empty medium where the BAP is 5 mg per liter concentration. So in this elongated shoots are 2.76. So we can say that the ground DNA is having this optimum level of what we call the BAP of about the 5 mg only. So optimum level of BAP concentration is 5 mg. If it is beyond that, then there is a what we call necrosis of found, and then there is a reduced production of the elongated shoots. Then this is monthon in which we have recorded this the average number of elongated shoots. So in this M2 medium is a very effective one. So it has recorded 3.90. So empty medium in which 5 mg per liter of BAP. So this is followed by M4 medium in which the 2 BAP mg is employed. So in this case 2.43 elongated shoots we have recorded. So in the monthon we can say the optimum level of BAP concentration is a 0.5, the 5 mg per liter. So here the growth response is excellent. So in this the culture quality is excellent one. So there is no blocking also in the monthon type of the cultivar, monthon cultivar. Then this is the red banana in which the VAP, the M1 medium is recording high level of this elongated shoots, high number of elongated shoots, in which 10 mg per liter is employed. So the culture quality is excellent one. Growth response is recorded within the 2 to 3 weeks time. So this the M1 medium, that means the 10 mg BAP is used here. The optimal level of concentration of the BAP in red banana is 10 mg. Then so after attaining some height of this planted, so these are transferred to the MS basal medium supplemented with 1% activated charcoal and then 1 mg of BAP for further shoot elongation rooting. Of course, in a manthan and red banana, so this concentration of BAP may not be sufficient one, but still you can see in the second cycle, second multiplication cycle is needed for further shoot elongation and rooting. So after that, the plants which are attaining these shoots and roots and all that, so these plants are transferred to the greenhouse conditions for hardening. So here the specially designed polyhouses are there. So in which the high humidity is maintained. So hardening is performed in the polyhouses. So like this, so this is the G9 banana cultivar. 30 days of the G9 banana cultivar grown in this polyhouse. Then clonal genetic validity studies here. Already I mentioned in the earlier that 6 primers have been employed here. So here you can see this number of bands recorded in the in vitro derived plants as well as in mother plant. Among this, the UGC primers, UGC, ISSR, UBC primers, 840 number primer is showing highest number of bands here, followed by the 808 primer, which is having this 138 number of bands in the manthan cultivar. Similarly, in the mother plant also showing highest number of 4 bands, 26, then 24, like this. So the total number of bands are recorded here with respect to the in vitro derived plants as well as the mother plant. So these are the ISR banding pattern you can see of the PCR amplified products. In the manthan cultivar only manthan cultivar is given here. 6 primers they are showing this various banding pattern here. So based on the number of bands recorded here, so we have calculated the monomorphic information content and polymorphic information content. So MS values and then PS values are recorded here. So among these cultivars, the manthan shows the monomorphic MIC value is 64.51, whereas PAC polymorphic information content is having this 35.48. So based on this MIC and PAC values, you can say it is the true to type. Almost this is similar to that of the genetic similarity is similar to that of the what you call the mother plant, respect to mother plant. Then followed by grand DNA, where you find the MS value is 48.14, then PS value is 51.85. You can say this plant, this cultivar is almost 50% similarity. It shows the 50% similarity to the mother plant. Then, whereas the red banana, where we find a lot of variation, genetic variation, the MIC value is only as 21.56, but high PAC value it is recorded, say 78.43. There is a lot of genetic variation found in this red banana. between the in vitro derived plants and the mother plant. So efforts are being made to follow the stricter protocols to reduce this in vitro stress, and also to develop the what we call improved protocols to improve this banana saplings, quality of banana saplings, in order to supply them to the farming community. The genetic fidelity studies revealed that the Manthan is a true to type and almost similar to that of the mother plant, whereas G9 and the red banana, they showed a lot of variation here. So that's about my work. Thank you for your kind attention. I especially thank to the Professor Tamasiri for inviting me to this conference. So Dr. Tamasiri is a good friend of mine. I have been known to him for the last 10 years. Once again, I especially thank to organizing committee for inviting to this conference. Thank you one and all. Okay.
Thank you, Dr. Kasim, for your interesting presentation. Dr. Kasim has joined us on WebEx and will be able to answer questions from the audience. So please feel free to type your questions in the comment box. We do have a couple of questions already, and the first one is from Dr. Kasim. Dr. Kasim has joined us on WebEx and will be able to answer questions from the audience. So the question from Dr. Kanchit Tamasiri is, how many varieties of banana do people grow commercially? And maybe if we can get help from the host to unmute his microphone for him. Dr. Kasim, are you able to turn on your microphone?
Hello.
All right, we can hear you now. So just to repeat the question, Dr. Tamasiri asked, how many varieties of banana do people grow commercially?
Hello.
Dr. Kasim, can you hear me?
Are you hearing me?
Your sound is a little choppy. Maybe you can try turning off your camera.
I think we can hear you now. Hello.
So there is an internet problem here. Internet problem. Move. Huh?
I think we may repeat the question again.
Okay, Dr. Kasim, can you hear me?
Yeah.
Okay, so the question was,
Please ask me.
the question from Dr. Tamasiri is,
Okay.
how many varieties of banana do people grow commercially?
So here we have investigated 3 cultivars of pizza. So this is, we have developed this in vitro derived plants, and also we have studied the genetic validity of this in vitro derived plants and compare this data with that of the mother plant. So this data, we have seen this the what you call red banana shows a lot of variation, genetic variation. So which is a lot of variation with that of mother plant. Only the only Manthan is a two fruit type. It is similar to that of the mother plant. So the thing is the red banana shows a lot of variation. So there is a lot of variation because of this soma clonal variation that is formed in the in vitro derived plants. So there must be the in vitro stress you find in the regenerated plants. So that's why there is a lot of genetic variation is recorded in this red banana. So in case of the grandine, there we find the 50% of the genetic similarity with that of the mother plant. So we have taken a lot of this stricter protocol. We are following the stricter protocol to reduce this in vitro stress, so as to have this high quality banana cultivars in order to supply this quality of banana to the farming community. So that is the reason, how this genetic variation found in this red banana because of this soma clonal variation. Okay. Are you satisfied with my answer? Hello?
Yes,
Elisa?
thank you for your answer.
Okay,
I have a
okay.
couple
Thank
more
you. Thanks a
questions.
lot.
I think the next one is from Dr. Sarod.
Oh, okay.
Okay.
Um, my question is now fungal disease is a very big problem in banana around the world. So do you think that banana in vitro collection in India can solve this problem?
So in India, no, the production capacity is very low. So, but the demand is very low. A lot of demand is there in India. So we need some 104, almost 104 billion plants in India. So there is a lot of gap in the production technology in this what we call the banana cultivars. So we have improved the protocols here. We have developed the protocols to meet the demand of these banana farmers in India. That's why we have taken work to develop the improved protocols. So to regenerate the plants, micropropagation of these banana cultivars. Okay.
Okay, thank you.
Okay. Thank you, sir.
And we have one more question from Andrea Rubenstein. How is the genetic variation that occurs during micropropagation benefit banana genetic improvement?
Well, banana has got a lot of therapeutic properties. In fact, it is a antioxidant property it has, and so it is very easy to digest, and it is very effective in treating the various cancer diseases like colorectal cancer, or then other what we call breast cancers, then carcinoma, other carcinoma cancers like this. So there is a lot of therapeutic property found in the banana fruit. Apart from this horticultural importance, then there is a medicinal importance we have in this banana. Okay, thank you, Elisa.
Thank you. That seems like those are all the questions that we have at the moment. So can we please give one more round of applause to Dr. Sim for his presentation and answers.
Okay, thank you. Thanks a lot.
And also, we just learned that Dr. Pei Xingji is also able to join us on WebEx now. So if anyone has questions for him, please feel free to type them in the chat box, in the comment box. We do have one question already, which is from Dr. Tamasiri. So can Dr. Patient please turn on his microphone?
Pardon, repeat the question.
Oh, Dr. Kasim, can you please turn off your microphone now? This question is for Dr. Patient. Okay. Dr. Patient, are you able to turn on your microphone, or can we have the host please help turn on the microphone? Dr. Patient, can you hear me?